when I was a student, I remember the first thing we had to make superconducting devices and, the theory. And a professor started the lecture with, now we're going to, study about Cooper pairs and BCS theory of superconductivity. And he said, this is the most important theory in physics in, 20th century. Well, take a wild guess. He was a condensed matter physicist when he said that. But jokes aside, this was a really rare idea that has changed the way we view physics or think about it for real. And, just to give you an example, which you're here today to hear how this idea changed even the way we see universe and black holes, supposedly, right? But to me, the most important thing is that idea after all these years has led even yet another Nobel Prize. It was this year's Nobel Prize. And basically principle of that theory now being used to make the most important of all superconducting devices that gave us qubits, in Google and IBM machines. So this is how far we came. But that theory reminds us that, deepest scientific advances often begin with a simple question that ends up transforming how we think about the world. And whether you work in biology, mathematics, engineering, art, whatever it is, story, this story really, or the purpose of our series is to show you, to offer you a glimpse of how imagination and collaboration can really unlock entirely new realm of understanding the nature around us, and how these moments of insight can ripple outwards, shaping technologies that I guess I care about the most, and ideas that define really our future. So without further ado, I'm going to give now the mic to my colleague, Professor Stefan Alexander, who's actually a director of this center, and to introduce the speaker. Thank you.
Thank you. And let's thank you, our wonderful chairperson, Vesna. She's been very, very supportive of the continuation of the center, the Phoenix moment. Thank you. First, I will be very short. I just want to thank a couple of people. First of all, I want to thank our founding director, Jim Gates, who's now actually on the scientific advisory board. He's a co-chair along with a Brown alum, Brian Keaton. And of course, the former director, Brad Mawson, who took us into where we are today, celebrating lots of cross collaborations. We want to thank, of course, our staff, Ariel Green, Valerie White, and Douglas for making all this happen. Instead, I actually prepared something because I knew I would be frozen. Leon played a very big role in my own life, and I wanted to just say a few words of why we want to commemorate this lecture series in his name. So just bear with me. We're doing it for him. So let me just pull this thing up, and I'll be fast. I will be fast. I promise you. But I have to first find it. Okay. And I forgot to bring my glasses. Does anybody have a 150? Oh, you are the man. Okay, here we go. Oh, by the way, I also want to welcome, we have lots of alums, physics alums actually on Zoom land. So welcome all physics alums, going way back like 30. Okay, and welcome. And welcome also members from other departments. We're much more a center for theoretical sciences. I know that makes Carly very happy. So let's begin. Good afternoon, everyone, and welcome to the inaugural Leon Cooper Lecture here at the Brown Center for Theoretical Sciences. Okay, and innovation is a big word, and that came out of the inspiration from Leon Cooper. It is deeply fitting that this lecture series bears Leon Cooper's name. Leon wasn't just a Nobel laureate for his groundbreaking work, as Vesna discussed, on superconductivity, and as we'll hear from our speaker. He was a visionary thinker who saw connections everywhere between physics and neuroscience, between theory and experiment, between ideas and their real-world implications. At Brown, he built bridges that stretch across disciplines, founding some of the earliest efforts in computational neuroscience, and even helping to launch one of the first AI companies. I actually now have been gifted that from Leon's estate the paperwork for Nestor. Nestor was one of the first AI companies founded at Brown by Leon and Charlie Albaum, who was another special person. Decades before machine learning became mainstream. But beyond his scientific brilliance, Leon left another legacy, one that's profoundly personal to many of us. He had a gift for mentorship. He saw potential in students who didn't yet see it in themselves. I was one of those students. When I first came to Brown in 1993, I wasn't sure I was smart enough or talented enough to do theoretical physics. Leon at the elevator rides, okay, a lot of those conversations happen in the elevators, taught me that imagination, curiosity, persistence were as vital to theory as the intellect itself. And just as important, Leon was never a theorist who stood apart from the lab. He loved working with experimentalists. He believed that theory and experiment complete each other, and that together they keep science alive and grounded. But in that same spirit, the Brown Center for Theoretical Physics and Science and Innovation is being built for all. For theorists, experimentalists, and creative thinkers across disciplines, we are an interdisciplinary effort, recognizing the importance of also focusing, right, and specializing. It's not either or, it's a both. So as we begin this lecture series, and we're going to have some really amazing speakers next year, wait till I tell you later on, after the person confirms. Yes. So as we begin this lecture series, we honor not only Leon Cooper's scientific achievements, but his example, his generosity, his interdisciplinary imagination, and his conviction that the next great ideas emerge when we dare to learn from one another. Thank you and welcome. Oh, one last thing. Please don't clap. Yeah. Okay. Another special person to many of us, my professor. I call him the master field theorist. Whenever I have a field theory question, I go to Antal. But Antal, you know, when he was hired, they came in three. We lost Leo Kadanoff, for those of you who know something about renormalization, to Chicago, and then three new faculty were hired, and I guess Antal was one of them. And the other one actually was someone that did win the Nobel Prize, another colleague, Mike Koselitz. And Leon was a part of that hiring. So I can't think of anybody more fitting, well, maybe Chung-Yi, to kind of give the inaugural Leon Cooper lecture than Professor Antal Jevicki.
And I have this. I think this should be working. Okay, great. Thank you, Stefan. Nice occasion. Great to be the first speaker. But when Stefan told me and asked me, he said, Antal, would you give the first seminar on your work? I said, yes. Then I received the title, and it turned out something different. So, but I'm very happy to give this talk on this occasion. Indeed, there is a lot of connection between what we are doing today and what was done in 1956 by Leon and others. So I hope I will be able to transmit how important it is to have this awareness and relationship between disciplines, and this what will follow will be actually a spectacular example of such a connection. Yeah. Okay. So the topic then is something in between the first. Let's see. I'm not sure I can. Oh, okay. The first topic of how important it was to have this influence of the BCS theory and other disciplines, in particular particle theory and gravity, out of which very successful theories of other interactions came with great experimental confirmation at LHC. But today we have a similar effort, which represents the understanding gravity, in particular quantum gravity, and forming something called the emergent theories of gravity. And the talk I would have given would be this last topic, and I might not come to that, on the collective structure of black holes. And indeed, that talk I gave when Leon was there, and I came here for the first time, was on a collective structure of hadrons. So it is almost the same subject, just you replace hadrons by black holes. And that already tells you that there is something going on through scales of physics where similar ideas will reappear again. And that is what we will see today. So let me start then with that introduction and just say a few words about, on this occasion, about this BCS theory and Cooper pairs. So that was the paper on the theory of superconductivity, 1957, July. And I should say that there was a lot of competition. There were papers before that. The subject was actually old, 1911, when the phenomena was observed. So there has been an increasing effort to understand how superconductivity works, why some materials are superconducting below some critical temperature. It turned out to be a very resilient problem, on which many failed. So Einstein, almost anyone who knew quantum mechanics was working on this problem at one point before this paper. And even this paper, there were other proposals and papers with the same title even. That is how dense the competition was. But that was the Nobel Prize then given for BCS for a successful understanding of what is the mechanism of superconductivity and how it works. And this is the plaque on the building in that, on the physics building at the University of Illinois. It says what you read, that John Bardeen, Leon Cooper, and Robert Schrieffer created the theory there in the building in this 1 year, 56, 57. And this is on the Register of Historic Sites of the American Physical Society. It should be of the US. But as I said, there were many other attempts even before. But, and one of them is here. That's the Landau-Ginzburg theory of superconductivity. Actually, this was also a successful attempt by Landau and Ginzburg. Ginzburg got the Nobel Prize for this later. It is a phenomenological theory. It's not as fundamental or doesn't go as deep to the understanding of the mechanism as the BCS. So that's why BCS was given the priority. Landau and Ginzburg are the ones who have written this series of theoretical books, I think 9 or so. They used to be a must for any graduate student in Russia at that time, or the Soviet Union. I don't think we can give those books today. We would be sued. Okay, and there was another attempt, and this is a New York Times front page, January 1st, as it says, 1958. So just and reporting from Moscow, where the Soviet Union every year would highlight the biggest achievements they had. Here they were Earth satellites that were launched and for which the people got Lenin medals, I think, Lenin prizes. But it was interesting that one of the, among next to these big achievements, it was also a new theory of superconductivity by the academician N.N. Bogolubov. And indeed, Bogolubov was working on that very closely, much like BCS. And there were also other groups which were working very intensively. So that is how intensive the competition was. again, the theory which Bogolyubov wrote, and he was aware of BCS in a way which he says, so there is no question of priority in that sense. But this theory was in a way different, although had some more mathematical ingredients which are used even today. Bogolyubov did get the Lenin Prize next year. And this is one of the participants from that big school in the Soviet Union, which has been spending already 10 years or longer on superfluidity and then superconductivity. And this is Lev Gorkov. There is a beautiful description of how much influence this theory had on them and what were the later developments which came from it. He ultimately was a professor here and got the Nobel Prize also. Most people who will be mentioned actually subsequently got the Nobel Prize, and they will all be related to BCS. So it tells you how important or how influential this theory was, or was to become. So that is Gorkov, his collaborator Abrikosov, who also got a Nobel Prize, will be mentioned again. 50 years of BCS. There's a beautiful book, a collection of original works and papers selected by Leon Cooper and Dima Feldman. It's a beautiful book, a very useful book. It also was named a top 5 book by Physics Today in 2011. So it does go and spends the time from 57 to a recent time when it was written, I don't know, 8 years ago, to 2011, and includes some of the implication on other fields. And here you mentioned nuclear physics, the quark plasma, and mentions even the Standard Model. I will be focusing or mentioning maybe the Standard Model more than anything else. But this is just to tell you that there will be, as years went, there were implications on many other fields. And fields which are also outside of physics, for which I don't have time to discuss. But let's go then to Leon Cooper. He got his high school, he finished high school at the Bronx High School of Science in 1947, and then went to study. His PhD was at Columbia University in particle physics, which will again be one of those elements that his degree and specialty was in something totally different than what the work or subject of BCS was, which was condensed matter physics. He spent a year at the Institute for Advanced Study, and then he was essentially recruited by John Bardeen to help out on this theory of superconductivity. Cooper was a field theorist, maybe specialist at that time in Feynman rules, Feynman diagrams, and Bardeen thought that method might be useful. By the way, this high school is well known for producing Nobel Prize winners. 1950, the two graduates who are Glashow and Weinberg got the Nobel Prize for this unified theory of weak and electromagnetic interactions. And in a way, it is very interesting that these two are just related by 3 years in the same high school, because one gave the theory of superconductivity, and the others gave a unified theory of weak electromagnetic interactions. And even that would be a coincidence. There were other Nobel Prize winners in the school, I think 10 or so. But these two subjects are very, very closely related, even though in different fields. So in a way, that will be a thrust or one of the main suggestions in this talk. So this was Cooper's paper when he was a postdoc at the Institute for Advanced Study. He says some notes on non-renormalizable field theories. In those days, there was a big success of quantum electrodynamics, electricity and magnetism at the quantum level. And that theory was shown to be renormalizable. You could calculate many things to some high degrees, and it was big success of that renormalization process. But other theories that particle physicists were interested in for weak interactions, that was a Fermi theory, or for strong interactions, that was a Yukawa theory, those were horribly divergent and in a way non-renormalizable. So indeed, this was a good thing to attack, good program to attack to make sense out of non-renormalizable theories. One should say that actually now there has been 70 years, but there has been no progress on that subject. So indeed, as a first year postdoc at Illinois, Leon changed the subjects drastically. And you can see from the both title and the style of the paper. So this is his paper on bound pairs. So that is the Cooper pair paper. It has 3 formulas as opposed to 78 in the other previous paper. It has 2.5, 1 page and a half if you count this as 2 pages here. So it is a remarkably short paper in the physical review, or rather letters to the editor in physical review. And it does give the mechanism of how electron pairs are formed, which was a subject rather central to understanding where superconductivity comes from. So this was the basic step of having the basic ingredient for understanding the next paper. So the Cooper pairing, and I will just be very schematic, takes into account 2 properties of electrons. So first of all, they're fermions that repel each other. So the ground states will be forming this so-called Fermi ball, where all the states in momentum space inside that ball are occupied. But then interesting things happen close to the Fermi surface. So it was very important to realize that things will happen close to the real Fermi surface, because electrons usually would repel each other, so very far away, not likely to form a pair. But it is that behavior near the Fermi surface. And another effect, which I think Bardeen was well aware of, which was the phonon interaction, which then made the force attractive. And based on these 2 ingredients and a little bit of linear algebra, Cooper was able to show that there is a pair formed. So those pairs obviously went a long way from those years of 56, when they were ingredients of this theory, and the manifestation of the theory was superconductivity. But today they can be photographed, and they really can be seen as pairs. So among the many electrons in this picture, you see that some which maybe are close enough, they will form a pair. So this has been done at MIT maybe last year. So with that, I think I explained a little bit what the background for the BCS theory was, the fact that you had this pair. The BCS theory was a field theory. Essentially, they were able to write down a field theory of non-relativistic kind. So electrons didn't have to move as fast as they would have moved at the LHC in the accelerator. They were slow moving, so you could use non-relativistic physics. But it was a field theory of those non-relativistic particles with that mechanism of forming pairs. And these pairs then would condense in its ground states. And that's where Bogolyubov's theory came, who also understood something about condensation for superfluidity also. But let me now turn to this connection of a totally different field, which is my field of particle theory. And Leon came here in 1962. I think he retired 10 years ago. At that time, when he retired, his books were available to be looked at and taken. So I took several books, which now that I had to prepare a talk, I looked up the books. What books has Leon? What has he been doing once he came to Brown? It turns out that he was going to nice meetings in the Mediterranean. That is really the joint topic. But it happens that those meetings are organized by particle physicists who have a habit of organizing meetings in fancy places. They have a long tradition of that. And one of these was in Erice in Sicily, and another was Cargese. So those were just two. There were many more of those. These were meetings strictly on particle physics, and the topics are very far removed from anything you might think Leon would be interested in. But his name is here. J.S. Bell is well known for some contributions to quantum mechanics. Okay, but at that time he was just doing some muon physics or some particle physics also. But in the first book, here is Leon's talk or lecture that he gave. It is very interesting to read the second paragraph or the first paragraph of this. It says there is little technical connection between this field and high energy theory in general, and but nevertheless he's apologetic, in fact very apologetic, that this lecture will be the price of admissions for these nice places, and that it will maybe offer some moral for particle physicists. When you read that, now I'm not sure how often has Leon been wrong, but he was very wrong on this, because what will come is that of all those papers of maybe high level particle theorists, they are all irrelevant today. And this is the only, if you took the book and said which papers are relevant today, this would be the only paper, meaning BCS. It's not particle physics, but it would be more relevant than those papers which were written in particle theory, or because things this year are beginning to change. So particle physics was in the following situation. Forces of electrons and photons were nicely understood. That was a big success of Tomonaga, Schwinger, and quantum electrodynamics was a field theory where the divergences were tamed and nicely renormalizable. You could then calculate using perturbation theory and get very precise results. In fact, this is the fine structure constant, and you can see that there are maybe today 11 decimal points which agree with the experiment. So such success is remarkable, taking into account that originally the theory was infinite. So it required subtractions, and if you subtract infinity from infinity, it will, you can always make a small mistake or even a big one. So it is a remarkable success of this quantum electrodynamics that it worked. So Feynman, Schwinger, and Tomonaga. And Feynman was the one who after that tried to understand superconductivity, but in that he failed. So he admitted that later. But the other interactions, the weak, were in horrible state. There was a Fermi model, the theory was non-normalizable, everything you calculate is infinite and couldn't be made of any sense. The strong were even worse. If you calculate in perturbation theory, everything is infinite, but even the coupling is supposed to be large. So the question of doing perturbation theory already is obsolete. So that is a totally no. So we didn't have a theory of strong interactions, and gravity, quantization of gravity that you wouldn't even mention. You would not be sane if you would not be considered sane if you talked about quantizing gravity in this age. Gravity was supposed to be a classical theory, and that's about it. So all these interactions were in a totally either horrible state, or even there is a question whether you should use quantum mechanics to address the last one. But then new things happened, and those new things were directly influenced by the BCS theory. So I don't know whether Nambu was there at any of those summer schools. He was maybe older, or as old as Leon or something similar, but he learned superconductivity very much. And one of the things Nambu did is understood the mechanism of symmetry breaking, which is present in the superconductor. And he came up with models, Nambu Journal-Lasigno model of symmetry breaking in a relativistic setup. And this will turn out to be a crucial ingredient of the unified theory, which is to come. So this is a picture of having symmetry breaking, the fact that we cannot sit on the top of this hat, but we are circling around this valley of the Mexican hat. And that circling around the valley creates a massless, or rather easily moving particle. That is called the Nambu-Goldstone boson. Goldstone was also the one who understood it. But the mechanism for this hat is essentially coming from the fact that you have symmetry breaking. For this, he did get a Nobel Prize at a later time, but this was a relativistic version of Landau-Ginzburg's theory, who had a similar phenomenological description of superconductivity. So that was one huge generalization, which will be directed toward particle physics, but not visible as yet that it has any usefulness in particle physics. That is to come. There was another ingredient, and this was maybe even more important, by Philip Anderson, a condensed matter theorist, and also a Nobel Prize winner for disordered systems, something totally different from at least this version of BCS theory. But he was an expert on BCS. There was a question in BCS theory, and that was a question of gauge invariance, electricity. Maxwell's theory and photons have this property, the very special property of gauge invariance. BCS, even though Cooper certainly knew gauge symmetry very well, but they didn't bother to spend time on analyzing that. They had much more important things to discuss, which was connection with experiment and agreeing with experiment. But there was a theoretical issue of the gauge invariance. What happens to gauge symmetry? And that question turned out to be actually fairly deep. Something indeed happens to this gauge symmetry, which is very striking and remarkable. And that was understood by Anderson. He understood that the photon essentially inside the superconductor, if I can say it that way, gets a mass. And up to that point, first of all, no one was interested in giving photon a mass. There were no massive photons roaming. We were very happy with the massless photons. That was quantum electrodynamics. So it was kind of an oddity that this happens in the superconductor case. This was also understood by Schwinger, but only in 2 dimensions, which is a bit trivial. But anyway, there was a mechanism for photon to get a mass. And based on those two ingredients, the Higgs mechanism was formed. And by this time, everyone learned that it is useful to take lessons from superconductivity. So all these people who participated in the development of Higgs mechanism, which were Braut, Englert, Higgs, and then we had Guralnik here, Hagen, and Kibble. So there were essentially 6 people, although Wikipedia adds even 'T-Hooft, which is correct, 7, Eberle and Rice, 8, 9. So the crowded, the idea, the things became crowded. I don't want to say it, but maybe because things were becoming very clear. So there was no big mystery. You put together the previous 2 slides from Nambu's symmetry breaking and just copy pages from one and another, put it together and publish a paper. That is the Higgs mechanism. So it's a very easy. You could actually just copy one page from one, another page from another, and claim a result. And that was the Higgs paper. Nevertheless, it was of great relevance for the upcoming theory. It doesn't matter how easy it was to get some knowledge, but if the knowledge is very important, we certainly are very, very, very impressed by that. So, by the way, among this, I think Jerry Guralnik once told me that he really never studied superconductivity. So he came up with this idea, not influenced by superconductivity, but it was easier if you already knew the phenomena in superconductivity. Guralnik was a student at Harvard, so that's understood and understandable. Because Schrieffer was a professor there and he had a field theoretic way of going about this mass generation. So he was influenced by that. In fact, I remember throughout his years here, he always used Schringer's lecture notes in the courses that he taught. So that's how influenced he was. But let's go, that's the Higgs mechanism. And based on that, there was a remarkable set of generalizations by Glashow, one of those high school buddies of Leon Cooper, and Weinberg, another one, which extended this by including Young-Mills theory, and that was then the beginning, the forming of this unified theory of weak and electromagnetic interactions. And by 67, Weinberg and Salam have written down this unified theory. So it was a very short time from those days of total chaos and zero understanding of anything in that Eriche school in 64 to just 67 where the theory of weak interactions was understood. And not only understood, but beautifully understood with unification with that theory of electricity, magnetism, and with huge number of predictions. After that, it was all experiment. Theory was finished, that unified theory is done, and it was a question. The experiment came very quickly, that there were W and Z, the massive photons were discovered, which was remarkable at LHC. And but the Higgs stood a little bit longer, and we all celebrated not that long ago when Higgs was discovered with great effort and I don't know, $20 billion. So this is a certain Courier where Weinberg at one point gave his reflection of what happened and how this theory was accomplished, the great grand unified theory of weak and electromagnetic interaction. And his title indeed was much like the title I gave. And I didn't know that just when I was searching for places which would maybe acknowledge the connection. But Weinberg acknowledges directly. His title of his summary is From BCS to LHC. So indeed, that is what went on. It was a trip from BCS to LHC. And I'm not sure which one is a greater theory. in many ways, this theory, unified theory of weak and electromagnetic interactions might be fundamentally greater than the model of BCS. The BCS is maybe, it might be called a theory, it's more of a model. The art of that model is that they isolated the important degrees of freedom, the important forces, and that was highly non-trivial, which then produced the effect. And in physics, that is sometimes a much better approach than trying to work much like Bogolyubov did from some basic theory, but the way to experiment is very long and complicated. So BCS showed how you can do that very effectively and get the theory with the smallest number of degrees of freedom, which gives you the biggest amount of data. So that is maybe what you would like to do. Ah, okay, yeah, that's right. So I'm not totally sure that this cow was spherical, but, but it's much simpler than the original fundamental theory. Okay, I at this point, probably you can guess that I am somewhere close to the, to maybe trying to give some evidence that BCS theory had some influence on other fields. Okay, in fact, it is true that it had just not the major influence. So at this point, then we are here. The theories of weak interactions and electromagnetic interactions are given by these groups, U1 and SU2, essentially. And those matter fields were coupled with a Young-Mills field, which was another huge generalization of Maxwell's electricity magnetism. Young just died maybe recently, but Young-Mills theory will be appearing everywhere. So all interactions of the world are given by Young-Mills theory, and that is the glue which holds everything together. So that is a topic for another lecture. That was not governed by some previous successful physics in condensed matter or other fields of science. This was governed by just mathematical elegance of constructing something symmetric. This is a high degree of symmetry, and that's how Young and Mills constructed this theory. But it is a part of that weak theory of weak and electromagnetic interactions. And at the same time, in 72 or 3, by applying Young-Mills theory with a color group, the strong interactions were supposed to be governed by this theory, just by Young-Mills, coupled to things which are called quarks. And quarks come with different colors, charges, isospin, strangeness. So some quantum numbers, and there are quarks, up, down, strange. And there is a whole zoo of quarks based on which the hadrons are formed. And the hadrons are, the simplest example are massive mesons. And here you see pairs again. All these mesons are, this is a pair of strange, and there are another pair of quarks here. And all observable particles are obtained as pairs. So in some sense, it's like Cooper pairing. But this pairing was very challenging to understand. Quarks were not observed experimentally in nature, so they would only come with this pairing, and the pairing had to be very, very strong. So strong that electrons you can observe separately. It's not only the Cooper pair which exists in nature. But in this case, mesons exist in nature, but quarks separately do not exist at all. So that was the proposal. Obviously, the way it will happen is that these quarks must be confined with a very strong linear force. But if you looked at that Young-Mills theory, the force was very weak and not linear at all. And it was understood that you have to solve that theory almost exactly. And that's what people did. They put it on a computer. And there are huge efforts which went on for the last 30 years. And quarks are indeed confined. Numerical results show that. That is called lattice gauge theory. There was an attempt to understand quark confinement in a physical sense. So one basic idea, which is true, that there should be some kind of string binding the quarks, and then they will not separate. The string will stretch, and the linear force will form. So this would be a pion between quark and an anti-quark, and this would be a baryon, a proton, which has 3 of them. Those are also strings, but a very funny kind. Now, this was just a picture, but the actual physical mechanism of how this would happen, that was also understood. And interestingly enough, so this is almost the last interaction we have, the strong interactions. It was understood that the strings will be formed as flux tubes. And that QCD, the vacuum, is a dual superconductor. So we just cannot get rid of BCS. Namely, it was the following phenomena was understood in superconductivity. And that phenomena is pictured down here. That if you have a magnetic monopole simulated by this solenoid and an anti-monopole, there will be a flux, electric flux, which will go in between. And this monopoles, magnetic monopoles, are confined. And particle physicists just inverted the picture. Because quarks carry charge, so they said the vacuum of QCD will be dual. Everything electric you replace by magnetic. And in that case, then the flux line the magnetic flux line will be formed, and then the quarks will be confined. So this just changed electric for magnetic, and out of that came a very convincing picture why quarks in QCD are confined. So this is still, so that obviously was a total copy of what went on in BCS. This copy was done by Nambu, whom we already mentioned, and you see the same players always appearing for good reason. And that is that's why we believe quark confinement. There is a prize at Harvard by the Clay Institute, whoever proves that this is a mathematical prize, I feel I should mention it to people, whoever proves quark confinement rigorously, you will get $1 million. No one yet claimed the prize. And we come to this question, which was supposed to be my talk, really. So I don't know whether we have time for anything. Yeah, well. So the question of gravity, and from all this, you see that these interactions of particle physics were understood one after another very quickly with great insight from that condensed matter logic. And that is a question of gravity. And you might say that here, that story, it ends. You cannot just go forever borrowing from your neighbors, or and also physics shouldn't be working like that. So the question of gravity. Gravity was a great theory. Einstein's theory of general relativity. It was not a gauge theory in the sense of Young-Mills or electricity magnetism. It had some other symmetries, but much more non-trivial, actually. The symmetry of coordinate transformations, where x in space can be a space-time, can be replaced by any function of space-time. This is still confusing to even mention that kind of symmetry, that those are equivalent. But that is the symmetry of GR. It is a very large symmetry, and that already might tell you that there is something special going to go on in this theory. The smaller the symmetry, the more obvious the theory is. The larger the symmetry, the more hidden the actual world is coming from a theory. But this GR had some beautiful, these are studied obviously at the classical level. It has some very beautiful solutions, the black hole and cosmologies, which are all of relevance and studied in astrophysical setting also. We had great results in observation in this. But when people studied black holes at essentially quantum level, what happened is they had to, first of all, it was obvious that they have some temperature. And Bekenstein and Hawking showed that black holes, much like black bodies, they radiate because they have temperature, so they radiate, and they have entropy. And this set of properties of black hole is absolutely confusing for a classical solution in any theory. You will never have a classical solution of some mechanical problem or something like that, and which will have entropy and the object will radiate. This is absolutely not possible. There was also a property of the black hole that there is a circle at some distance related to that mass of the black hole that that's called the horizon, and the horizon is really something which leads to many paradoxes. So the horizon is where space changes into time, which is not something we do. If you are walking and your next step will now, you think you are just making one step in space, but you are moving in time along that direction. And related to that, at quantum level, that led to information loss, that things would fall in and never come back. So I think I'm missing the lower portion of this. So it led to suggestions that this is all in contradiction with quantum mechanics. Black holes should not be quantized, or it is in contradiction that space-time is local, that we have locality. There's some maybe weird non-locality. So there were many suggestions to solve this problem. Apart from that, the theory is absolutely infinite. So any attempts to compute in perturbation theory, it is an absolutely infinite theory. Interestingly, the resolution of what will happen to gravity, or what the resolution of all this is provided by the theory itself. Very often does the theory provide both the paradox and the resolution to the paradox. Often there is a paradox, you have to give up the theory, or you never are so fortunate that the resolution was also related to some property of the black hole. And the property is very simple. Because it's thermal, it has entropy. And when Hawking and Bekenstein computed that entropy, it happened to be precisely related to the area of this horizon. Okay. And this is very unusual because in condensed matter physics or in field theory, entropy will always be related to the volume of the thing. So this is violating, or this is different. In that sense, the black holes are different than any other object you will find in the universe, that the entropy is related to the area. And in a way, this property gave the clue what is going on. If you think about it a little bit or longer, the clue is there. it says that Einstein's gravity, so it led to the word holography, that the actual theory is not to be specified in 3+1 dimension, not in three-dimensional space-time, but maybe in two or lesser dimensions, which would then explain this entropy, which is much smaller. It lives only on the surface of this black hole. So if you wanted to do gravity, you should not be looking at Einstein's theory where this black hole came from. You should be looking at some lower dimensional theories, and then you should try to see how black holes will emerge and how your space-time will emerge, because the theory is in lower dimension. You have to account for our space-time. So you have to first account for the space-time and then for the black hole itself. Looks to be a crazy suggestion, but that was suggested by Susskind and Hawking and Tuft. So we understood, so this was maybe not a positive understanding at the beginning, that we should not think of Einstein's gravity as a fundamental theory. It is rather some kind of emergent description. Even space-time is emergent, so we should not be even thinking that we are to study something which is in 3+1 dimension, which we should study something in lesser dimension. Now, some understanding of gravity came from string theory. Now, string theory had more than 4 dimensions, so I don't like to mention it too much because it goes in the other direction. It only exists in 10 dimensions and 26, even though it is sick. But I will mention one which is really our theory of gravity, and that's called the matrix theory. And also the fact that black holes themselves, black hole is a hologram. So these two ideas are rather well established. So I will just give you one thing, which is how this matrix theory looks like. It looks like very much like Young-Mills theory, but in 0 spatial dimensions. So just time, these fields here, which are called X, but they only depend on time, but they are very, very large matrices. And this has nothing visibly to do in appearance with general relativity as we know it. But likewise, the bunch of electrons which Leon Cooper studied first, that has nothing to do with the superconductivity that he observed. That was observed. That was a collective phenomena coming from many, many electrons with a mechanism of pairing, which also played a role. So there is a long way from the microscopic theory and what we observed. That's one thing we learned from Cooper. So in this case, our theory is that of 9 matrices, n by n, and n is supposed to be very large. You probably can expect that if the matrices are large enough, you can package into that anything you want. Now, you know, huge matrices will do. So in some sense, maybe that's the truth. I think I have only a couple things to mention, and that will be the following. There is a model known as Jevicki model, which shows actually how that happens. We often learn a lot from simple models. This has been studying even now. At the heart of the model is, again, a pair. The pairs still keep coming back. And this is now a pair in time. Leon Cooper's pair is in momentum space, and this is a pair in time. And that's how gravity might emerge. I will skip. There is a mapping from those matrices to the black hole itself. This is the black hole space-time. I mentioned that our fundamental theory is not in that space-time. So that mapping turns out to be very similar to it's called the radon mapping in applied mathematics. For totally unknown reason, it's the same mapping used in CAT scans, in reconstructing your brain. That's just an anecdote, or that's just for some reason the same mathematics is used. But out of this understanding, there came models of black holes, or what the black holes are made from. One of the very popular one is that it's a fuzzball of ingredients which you have to study. In my popular pursuit is that we can go from matrices to black holes using words, namely matrices. One, call it A, two, call it B, C, third, call it C. The observables are traces of matrices. That makes sense because you want numbers, not matrices. And you can start forming the words AB, AB, AC, AA, B, C, D, and that would be a word. So we are now studying many-body problem of words, much like Cooper studied many-body problem of electrons. And looks interesting. To compute the black hole entropy, you have to form a black hole out of those infinitely many words that obviously that go to infinity. There are infinitely many words. You now have to select those words which you think are good candidates to make a black hole. So we are now looking at what makes a black hole. And we have managed to give some criteria for what makes a good state to form a black hole. It's called fortuity, as if there is anything fortunate about being an ingredient of a black hole. You never will come out, but nevertheless, this ingredient is called fortuity. So only fortuitous words are used to become ingredients of black hole. Obviously, this is a little bit of a comic book, but this calculation is not, okay? When we go and start calculating the number of those words, which we call fortuitous, and we could calculate them for n, the size of matrices being 5, 6, and 7. We cannot go up because the number of words grows horrendously. And we get this curve for the number of words. And the log of that number will be the entropy. And that way you find a number that it is equal to e to the n squared. I forgot to mention that n squared in that model of gravity is related to Newton's constant. And if you remember the entropy of black hole, which came from Hawking, Bekenstein, I at one point stated it, C was the area and some other numbers, but the denominator was Newton's constant. So this calculation of counting words, special words, very, very special words, how special, that 10 million words which declare themselves, oh, I am a graviton, so don't count me in. And then you find one which says I am a black hole, and that you separate. It is even smaller number than that you have to identify. So you are identifying a very, very small number among a hugely infinite number. But once you identify it, that number reproduces the Hawking-Bekenstein entropy. So with this, I hope I gave some flavor of. First, this was not only a flavor, that was just a legacy of Cooper and BCS theory of how directly it influenced others, but how directly it continues to influence our way of thinking, that most of the structures we have, including black holes, represent the collective dynamics, much like the collective dynamics behind the BCS theory. So thank you.
So we have some time for some questions, and you pass the microphone.
So this is being recorded. So if you have a question, just speak it.
Come on, let's not be shy here.
I don't know what the record is for the most different fields to study 150-minute talk, but that's pretty amazing. Why did you say that you couldn't create entropy for a classical system?
No, I didn't. Sorry, I didn't mean that. You can. That's true. But this entropy is quantum mechanical. So in that formula of Bekenstein, there is a 1 over h bar. So it must be a quantum mechanical reconstruction of entropy.
So h bar makes it quantum, even
That's
if,
right.
even if variables are continuous?
No, it has to be found in quantum mechanics. So that sorry, I meant in a way that.
I think Max had a question like that. And while Max is getting, I want to make a very quick announcement. So we'll be having these Leon Cooper seminars next semester. We'll probably have 2. But we're also going to have another event called Innovate Salon. It's a salon series, like smaller talks, like TED-like talks, featuring BCTPI members. And then we're going to have a special one by our very own Professor Karina Curto in applied math and neuroscience. Amazing work. And we will announce that. And that is going to actually be a little bit of a part, you know what I'm saying, like wine and cheese and entertainment. So we will be announcing that. So stay afloat for that. And now Max, that's perfect.
When you say you construct a black hole state or you construct a graviton state from these sequences of words, are you constructing, is this like a coherent state that whose like the expectation value of like
the graviton state would just be a regular state, but the black hole will be a coherent state, and in fact it has to be a thermal coherent state, so it's even more than that. So a black hole is much more complicated than just one state. Here you could see that you have to use e to the n squared number of these states. So it's an ensemble of states which make that fuzzball that I drew at one point. Okay.
Thank you. And then could I ask one more question as well? Yeah. What's the moral we should draw from Bogoliubov's story?
No, you did get the Lenin Prize. No, there is some moral there because there were other attempts. It was the theory was maybe too fundamental. He was starting with ingredients which are actually more fundamental. He used phonons in his Lagrangian and so on, and that makes your predictions more difficult. But it actually was a good theory. And at one point, for example, Landau and Ginzburg's theory was very phenomenological, the opposite end. And that was really derived from BCS.
Maybe your guess is right.
Okay.
Right.
No, just write the state. Wave function.
Thank you, Professor Jevicki, for the wonderful talk. I have a question regarding the legacy of BCS theory. There's many interest in the field of machine learning. They're talking about emergent phenomena in large language model. Do you think BCS could be the important ingredients to tackle down the emergent phenomena in machine learning or deep learning?
Right. I'm not sure that way. It as Leon Cooper said, it might be just showing you the morale, the way of how you should do, but it doesn't mean it will operate precisely the same way. So, for example, this last topic of black hole interior and reconstructing black holes obviously uses a totally different set of ingredients, totally different forces. They are not pairs anymore. Now you have these words put together. So it's just that far that you can go directly and with applying BCS directly to your problem.
Well, thanks for this wonderful talk. Now, you did mention at some point toward the end, you said string theory involves too many dimensions, so therefore you want to avoid it.
Yeah.
Do you avoid for this talk or just avoid it in physics?
No, not only for this talk. Maybe the last 15 years I have been avoiding it. No, it is a nice theory, but it might detract you from what is really the important problem. So it's maybe tries to make solve the problem too easily, but then you do not know what black holes are made from. You will not be able to resolve the information paradox. So maybe this other line of thinking, which is condensed matter, may be more promising for resolving some. String theory did not help to resolve the big paradox of information loss. For that,
Can it also be a phenomenological theory of some sort?
Not for this purpose, for making a black hole. So it's still a fundamental theory. It's too fundamental in a way. It's too fundamental. So.
One more question, or somebody's burning to ask another more question.
Thank you for the great talk, Professor Jevicki. Is there an observational way to test Hawking's prediction that black holes have a temperature?
People are now trying to see what would be the signatures of a horizon. So it would be observing the horizon, and that is very difficult at this point because you have to make a prediction of what. So there might be. So the standard law of just GR is that nothing really happens as you cross the horizon. So that way, that's unlikely that you'll be observing anything, especially from this distance where those black holes are. But the fuzzball picture tells you that there is something in there. So that is a different scenario which might have a prediction which differentiates the fuzzball from this empty space black hole. And that might lead to testing.
Thank you.
Well, my last question.
Thank you for the talk, Professor Jevicki. Going back to this notion of these words inside of black holes, is it possible to draw analogies between this formulation and also other natural codes in nature like DNA or RNA and things like that by chance?
Yeah, maybe you say there are some patterns and so on. Maybe you should try.
Thank you.
It would be great. But yeah, there is some big resemblance that there is some code. Yeah.
So we'll end with thank you. I'm going to end with a Leon Cooper story. So Leon would like to often confront students in the elevator rides. So we'd be in the elevators, and he would come in the elevator. And oftentimes, when we go to the elevator in Barris and Holley, people are quiet. No one talks, right? All right, so you get off, all of a sudden Leon will get in the elevator and then start asking you questions. Oh, so what do you think? You go up to the 7th floor, right? What are you thinking about? I'm thinking about this. Then this would go on for a while. Go into the elevator. What are you thinking about? And finally, you muster up the courage to really get excited about what you're thinking about. Oh yeah, I'm thinking about this, and I'm working on this. Whatever you go, and then right before the elevator closes and he leaves, he would look at you and go, "Do you really believe in what you're working on?" And then and that stuck me for the rest of my life. I don't believe in anything I work on. Okay, on that note, stay tuned for more fun events with the center, and faculty and our guests are invited to the 7th floor, 723 for soda.